of Material Science and Technology at IIT BHU. Um, we together started in 2000, not 2096 to 98 in masters in BHU. Then we ended up doing PhD together from IIT Kanpur 98 to roughly 2004, maybe four. He got out for a postdoc. And then we joined together in Banaras Hindu University as faculty. So I left it in between in a couple of months. Chandan is now a senior associate professor there in School of Material Science. So he'll be talking about the magnetic data storage, the materials aspects. And there's a lot to learn about that.
Yeah, hello.
Device physics. This is complementary in the sense that this is also used in electronics industry, but in our syllabus, this is not covered. So I hope this will give you some other perspective also in the billions of dollars electronics industry. With that, I'll invite Chandan to walk us through his lecture.
Thank you, Rajan. It's always a pleasure to talk to the students. I don't know if we can make it interactive or not, but if some of the student can answer the questions or keep giving the feedback, and if there is a question, please raise your hand. So probably that will be fantastic. Okay.
Something what happened, I wanted to make it that way, but I probably did not communicate it. Everybody is in different locations. I thought they will get together in the class and then I'll project and we'll have interactive, but while I was going, some students told me that nobody is in the class, so I had to last minute come back.
No problem.
And we are all scattered, yeah. So
I mean, those who can, in a location where from there they can speak, they can, they can ask questions and answer the questions and all. So anyway, so I'm showing you something. Let me bring it closer to the screen. How many of you recognize this? Just raise your hand. Okay, quite a number.
Yeah, and you can probably double click on the screen and make it bigger size. I think his screen, so it will be bigger, I guess.
I hope that the students are, on the bigger screen. Okay, so you know, in the chat box, you can write it that what I have shown. Just to warm you up. Okay, very nice. Can someone, it's not a flippy disk, it's a floppy disk. Okay, yeah, okay, fine. So some of you can tell me that what is the capacity of these floppy disks, if it's possible. Anyone? 32 MB. Shrestha, your hand is raised, you can also speak. Anyone else? What is the capacity of this floppy disk?
2 MB.
2 MB, okay. Anyone else? So anyway, so what we are dealing here with is having a capacity of 1.44 MB probably. Okay. So I think that is rather this. And what is the dimension? Is 3.5 inches dia. Okay. So I give you assignment number 1, that you calculate, that the area required for 1 bit. Fine. I mean that you do it on your own. Fine. Then let me ask you another question. You people might be using, your laptop or computer. Can you tell me that what is the capacity of your hard disk now? Class, use the chat box. What is the capacity of the hard disk which you are using right now? Okay, super cool. Anyone else? 1 TB, fine. So we have gone from 1.44 MB to 1.5 TB. Okay. So how many fold of increase? Mega to tera. So we have increased, 10 to the power 6 times. Fine, is that okay? Class. Yeah, Rajan, you can mute yourself.
I am unmuted. You want to?
No. There's some background noise is there. Okay. So there is an increase in the size of the order of 10 to the power 6 times. So if we go by some lateral calculation, the area per bit has gone 10 to the power 3 times. Okay. So there is a huge reduction. Okay, so this information we will use it later sometime. But the thing is that the technology has progressed so much that we have gone to a storage of 10 to the power 6 times. Fine. Number 1 information. The second information is that there is a continuous progress. Now I will present the screen. Can you see it? Class? Is it visible to you? Okay. So the story started, somewhere around 60s. So we had the first hard disk, and then, the areal density is on the Y scale. So it has gone quite a bit, and now one can store up to 10 to the power 6 megabits per square inch. So that's the capacity right now. Okay. So there is an increase of 17 million times of annual fold, and then the growth is 100% annual growth rate, which is quite a big number. And the good part is that this is how a hard disk looks like. Fine, and 3.5 inches dia. The technology, one aspect has not changed, that the hard disk size is roughly of the order of it's the same 3.5 MB, and this is how internally it looks like. There is a head arm, there is a head actuator, there is a disk platter, there is mounting chassis, and then read write head, we will be talking about this as well, and then the mounting holes. Fine. Okay, so coming back to the so what these materials are. Okay, how many of you remember a cassette, audio cassette? Any one of you have used it? Okay, fine, super cool. So what an audio cassette does, that there is a small polymer tape, okay, and then on this there is a material which is generally magnetic material, and the data pattern is recorded on it. Okay, so for our purposes, for the floppy disk and the hard disk, in what form the data is needed in the form of 1 and 0. So we need to have two states, state 1 and state 2. All right. So when we have a magnetic material, so what we can, I think that this is very familiar curve to you all, that there is a magnetization in this direction and there is a magnetization in another direction. So I can safely say that there are two magnetization direction, one in somewhere and another in another direction. I can treat them as a 1 and 0. Okay. And let's see that what are the other requirements and everything else, so that we can familiarize with the recording technology. Is that okay up to this point? There was nothing, complicated. Fine? Okay, good. So, chalo. So, let's try to learn. So we start with, the data recording thing. So we know that, in order to orient a magnetic material, okay, we have to apply a magnetic field. Fine. So if I apply a magnetic field, then a magnetic material which is, having some spontaneous magnetization, that get oriented in a particular direction. How can we produce a magnetic field? We can produce a magnetic field by a solenoid coil. Fine. So if there is a current in this direction, fine, we can figure it out, and then this will exert a magnetic field direction like this, and then here we are, going like this. So if this is the direction of the magnetic field applied through a solenoid coil, what it will try to do is the same picture here. It will try to orient the material which we are having in a particular direction. Okay. And if I reverse the direction of the current, then what will happen? The magnetization direction, magnetic field direction of, which is getting generated out of the solenoid is also changed. And if I move this entire assembly somewhere over here, this entire thing is moved, or I have moved this guy over here and change the direction of the current, or in other word, the magnetization direction has also changed. So now we achieve that requirement. One magnetic direction like 1, another magnetic direction like 0. So if this is my 1, this will be 0. So that is the fundamental which is going, okay, in order to record the data in form of 1 and 0. Is that okay up to this point? Class? Fine. Okay. Now, let me ask you a question. That what is the Earth magnetic field? Shrestha Mishra, you have raised the hand. Is there any question? Shrestha? Okay, no issue.
I think this is generally raised hand.
Okay. So class, so what is the Earth magnetic field? Any clue? Anyone? hope that you must be having, some feel of the numbers. Should we stay here or should we move? Five Tesla. My goodness. Okay. So the Earth magnetic field is note it down somewhere, is from 0.25 to 0.65 Gauss. Okay. And 1 Gauss is 10 to the power minus 4 Tesla. Okay. So you can imagine that how feeble this magnetic field is. Okay. Can you realize the number now? Okay. No problem. So anyway, so the point is that these magnetic fields are really, really small, which we encounter on our day-to-day basis. Fine. And then what we have to do, we have to orient the entire material in a particular direction. Okay. So if I find something, let's say there are two scenarios, I am presenting it to you. Let me remove everything and ask you another question, that which one is preferable. So here is two scenario. In one scenario, I applied a magnetic field and then it got saturated. This value is around 3 to around, let's say, 10 or straight. Okay, or Gauss. And here we get something like this, and this value is of the order of 200 Gauss. Okay. So which field is easier to produce? 10 Gauss or 200 Gauss? Remember that, in order to get 200 Gauss, we have to have a really big solenoid and all this. So we really need a very, very, weak magnetic field. Fine. And that weak magnetic field we get it through some solenoid or some other method. Okay, through a permanent magnet or something like that. So one requirement for my magnetic material, if I want to use it for the data recording, that it should get saturated very fast. Okay, if you people are not aware about this language of the hysteresis, let me write it down for you. When we apply a magnetic field in a particular direction, okay, and the y-axis is called magnetization. Magnetization is that the strength of the, the magnetic polarization in one way. And then this is the applied field which is being done externally. So we do this. So the value on which that is not increasing anymore is called saturation magnetization. And because of some phenomena which we will not be discussing it over here. Okay. Sorry, if there will be no question, I have to go to that level. So this is called saturation magnetization. Note it down somewhere. And these all parameters are important. This value, when while coming back, we have zero field, and then still there is something remains there, is called remanent magnetization. And generally reported by are denoted by MR. This value by which applying in the another direction this value becomes 0 is called coercivity. And generally denoted by Hc. So we have to orient it. Okay. So orientation needs a very fast increase of the magnetization value with the application of the magnetic field. When something like this happens, we call it it has to be high permeability. Is it visible the screen?
No, sir.
Huh? Is the screen visible? Can I remove this? Or at least this? So the first requirement of the material is that it has to get polarized very, very fast. So my material on which I want to record some data 1 and 0, it should have high permeability. Now it has been, got oriented. But then I have to read it also. Okay. So if this value is really, really small, okay, it will not create a signal in the reading device. Okay. So we will learn about that as well. So the another requirement for the material is that it should have a high saturation magnetization. That if I orient it, it should give me a good value of the magnetization. Okay, so what it need is the high saturation magnetization. Okay, so two requirements are down there. Then let's say that I have recorded my things in form of 1 0 1 0 and all. Okay, and we keep on, we have to keep on using it again and again and again and again. So I have to destroy this and record it again. So let's say that now my bit, this is confined to this zone, has to be 0. Okay, so 0 means another orientation. So that means that it has to go in this direction. But before that, it has to get destroyed. Okay. So in order to destroy it, I have to have a 0 magnetization value. So this means that we have to reach here. Okay. And you note it down that, in order to create a huge field, we have to have a huge setup. So we have to have a small coercivity value or Hc value so that I can destroy that data so that I can record it again. Okay, so that's another requirement. So third requirement is a small value of coercivity, but I will hold here. Okay, value of coercivity. But what happened if there is some stray field from here and there, I mean some sparking happen or something, or even the earth magnetic field or something. Okay, if some stray field comes, so what it will do, it will try to orient this guy in some other direction. If it was earlier like this and then a stray field got applied in this direction, so what it will try to do, it will orient the bit in the another direction, and my data is lost. So it should not be a small value so that any stray field or anything can destroy this. Okay, so the small value is not needed. We have to have an optimum value. Okay, not big enough and not small enough as well. So now my material has to have three requirements: high permeability, high saturation magnetization, and optimum value of coercivity. Is it clear up to this point that why we need it? Class, is the all requirement clear up to this point? Okay. So we have to high permeability, high saturation membrane, optimum value of corrosivity. But then something else is also there. Okay. We need to have a trigger as well. Okay. Because what we are doing it after Ricarding, we are using it under no influence of external magnetic field. Okay. So our application is at the zero applied field. Okay. I mean, we recorded the data. I mean, after that we have to use it. So that means that the recording assembly has been removed and now we are reading it. So that means that the system will gradually come to a point where there is no magnetic field applied over here. Okay. So we are here under the actual application. Okay. So MR has to be also quite high. So number 4, that remanent magnetization should be okay. So when saturation magnetization is also high and remanent is also high, so let's say that how it will look like. Okay. So I'm going to remove it and redraw. So I know my all the requirement. Okay. So one requirement is that high permeability, high saturation magnetization, optimal level of porosity, remnant magnetization should be high. So now my hysteresis response will look something like this. Okay. So the loop has to be very squarish in nature, sorry, rectangular in nature. Okay. That there should not be any difference, or preferable is that there should not be any difference between MS and MR, but that's not possible. So it is like this. So the 5th requirement is rectangular hysteresis loop. So now we are left with high permeability, high saturation magnetization, optimum value of porosity, remnant magnetization, and rectangular hysteresis loop. So I mean, you might have experienced it on your own. Okay, that when you apply so many filters, we are left with very few choices. So in a similar fashion, for the material which can qualify for magnetic recording, we have a very few choices. I mean, a lot of materials are not available. Okay, for to be deployed as the recording material. Okay. So I mean, we will see that which kind of materials are available there. So is that okay up to this point? That what are the requirements for some material to get deployed for the recording? If there is any question or confusion, do let me know, because now here the mode will change. Feel free. So either it's going too well or it's going too bad. There is no question. Nikhil Sa. Nikhil. Sri Ram.
Nikhil was talking just now, right?
I think Nikhil is. Yeah, Nikhil.
So my device is malfunctioning.
Okay, good. Rajsri. Vignesh. मोनिशा, सारे कैंटीन में हैं क्या?
I don't know. I think they are probably shy.
No, they
The
should not be
class-
shy. I mean, why? There's no need to be shy.
Actually, this is my observation. What happens? I take class, and in the class, mostly they don't ask. But in a remedial class, there are few students. No, then they will have a lot of questions.
See, in my class, I force, people to ask questions. I mean, not force, but I encourage them to, Archit, how is the coffee? Are you around, Archit? या लॉगिन करके चले गए क्या?
Yes, I am there.
I think
Yeah, okay. So, chalo, Archit is there. So,
they are all they are MTech students. They are more sincere than BTech students.
I mean, sorry everywhere. So anyway, Archit, so is that okay up to this point? It's clear?
Yes, sir.
Okay. So have you seen the VCRs?
I'm not sure. I think for VCR is like more than 30 years, 20 years old, right?
You might have seen the cassettes, huh? No?
I think during my childhood it was, popular, but soon the CD players came. After that, they were completely eliminated.
Okay, so let me ask that question to someone else. How many of you have seen the VCR? Raise your hand. I will not ask another question. You have to just raise hand so that I can pick it from there. Piyush, okay. What was the difference between cassette and the VCR? The strip size. Okay, Kannam. What was the difference between VCR strip size and the cassette, normal audio cassette strip size? Anyone? Those who have seen it? Anyway, so I will show you some slides and then we'll discuss it there. So we have to record more and more data. So how it is being done, let's try to see it and then we will come back to the limits. So present. So fine, we are keep on recording more and more. Okay. But these requirement has to be fulfilled. So here it is. So now there are two kind of recording. Okay. One is known as perpendicular recording and one is longitudinal recording. So longitudinal recording, we have just discussed it out that there is one set of particle where there's one set of particle where everything is in a particular direction. That means that the north-south direction or magnetization direction is from here to here. Whereas for the other set of particles, the magnetization direction is slightly different. So that is kind of a longitudinal recording, okay, over a substrate layer. But then with the advent of the technology, it has moved to from longitudinal to perpendicular recording. Okay, so perpendicular recording means that now my data is recorded like a pillars. Okay, so this will be treated as 1, this will be treated as 0, depending on that how I have classified it. Okay, so now from the same size I can pack more and more data. Okay, so that was the first big step from longitudinal to perpendicular recording. Now it's possible to pack more and more data. Okay, so this is how it looks like. Okay, so this is a magnetic particles, real, actual real particles, magnetic materials possessing all these five properties. Okay, that they got recorded, and there's some kind of the other setups and other technological requirements are there. We will not go into the detail of that. Fine. So here it looked real one. Fine. So these are the grains. Okay. You may see a smaller grain over here. There's a bigger grain over here. Okay. And then when everything got magnetized, then they all have some sort of a oriented direction, and then the other set of the grains have the another kind of an orientation. So this is the real picture where one can do all kind of recording with surrounded by a layer which is separating one bit to another bit. So this is one bit, this is another bit. Okay, so I mean in case of a normal scenario, this is totally random. Fine. In case of another scenario, it's a 2D random, means that we have the kind of there's a preferred orientation. Here you may see this another guy in another direction. Here what is there, that they are towards a two-dimensional random, but that means that there's one directionality is down there. Okay, and gradually it's become oriented over here, and finally it is the ideal longitudinal media. Okay, so now here, so some calculation has been done. I will switch back to the so we have to pack more and more. Okay, so that means what we are doing is that we are increasing the packing density, and how we can do that, by decreasing the bit size. Okay, so one bit is now is using a really small area, but then we have this grain. Okay, if the grain size is bigger than the bit size required, what we have to do, we have to reduce the grain size as well. Okay, those grains which you have seen it. So now we have to have a smaller kind of a grain, which size is really now from micrometer to nanometer square. Okay, that has to be used. But then there come some problems, and that we are going to discuss now. Okay. Do you know that a normal piece of iron is non-magnetic? I mean, you cannot attract another nail with the help of a nail unless and until you magnetize it. You might have experienced it, right, class?
Yes.
Okay. Can you tell that why this happens? Okay, I mean, I will tell you that why this happens. You may not know. So here is why. Typical, let's say that I'm discussing, a big chunk of the one. Okay. So what happens, that this is divided into a different kind of a magnetic domain. Okay. So the magnetic domains are in such a way oriented that we find it, the total sum, vector sum of all, m vector is equal to 0. Okay. So if the total sum of all this, small magnetic domains are 0, there will be no magnetization. So this is nothing is down there. Okay, so it will not behave like the whole bunch. It will not behave like a magnet. So that's why it is not able to attract another nail. So this is what happens there. Okay, but if you look very closely and if you zoom this, okay, then how it looks like that? Let's try to see it. So I have zoomed this portion. So what is actually happening, that so it was like this, and suddenly you find that there's another guy. So if it's not like that there's a sudden change, okay, atomic at the atomic scale, this change is very gradual. So the another guy is oriented in this direction, another guy is oriented in this direction, another guy is oriented in another direction, and another direction, and then there is a flip. I'm just giving you the projection. Fine, the spin magnetic moment is same. It's just the projection. So it looks something like this. I mean, from going from one direction to another direction, it goes gradually from one to another. Okay. So this is known as domain wall. Okay. I mean, at what is the level of the second year student or third year student, Rajan?
No, these are MTech first year students.
Okay, MTech first year student. And the background is variable or background is...
Yes. Background is quite variable. They have triple E, EC, all kinds of background.
Okay. So I will write some equations for them. Just give me a second. That is important to realize that what is actually happening there. I mean, all you are familiar with the magnetic materials, right? A little bit. Hysteresis and all these terms you have already gone through, isn't it, class?
Yes, sir, little.
Yeah, okay. Good. So there is a domain wall. Okay. And you know that this spin half a magnetic moment, you might have gone through that spin half and all these things in your intermediate. Right? So each atom is let's say that I have yeah, there is a raised hand. Alam.
Sir, can you please repeat domain null?
Domain wall again.
Yes, so what is actually physical significance of domain null, sir?
Okay. First is significance of domain. So in the normal scenario, what happened that, okay, I'm coming to that. So in normal scenario, what happened that if we, let's say, magnetize everything, okay. So there is something called demagnetizing field. If everything is magnetized in a particular direction, then the energy state of this particular specimen where everything is aligned in a particular, all these spins are aligned in a particular direction, then they are in the higher energy state. Okay, so in order to minimize that higher energy state, what they do, they split it into different domains. So what it will do, it will, let's say, split into two domains, but still there is something is going on. Then it is split into again some sort of another domain. So now the magnetic lines are closed. Let's say that such a kind of a scenario arises. So the total demagnetizing field is now 0 for this. Okay. So the total demagnetization energy is also minimized. So the system always break into different domains. And when the domains actually get formed, it is not a sudden formation. Like, it's not like this that the one domain is having all the spins before that aligned in a particular direction and then suddenly everything is in the another direction. Okay, this scenario is not there. So when this scenario is not there, so how is the real scenario? The real scenario is that it gradually shifts from one direction to another direction. So from where the shifting starts, I mean, in this direction everything is aligned. In this direction everything is also aligned. But I have just zoomed this portion, from here to here. So from there to up to this point, this is known as domain wall. Okay, that is the wall between two domains, and this is a gradual change of the spin direction. Is that clear?
Yes, sir.
Okay. So there is something called stiffness. That stiffness means that how strongly attached they are to a particular direction. Fine. So that's the measure of the stiffness. Let me write down the expression only for you because it will be used later. Okay. So the stiffness constant is written as A, and this is S square, A square, J and by 2. Okay. So S is the spin magnetic moment. Need not to know a lot about it. A is the lattice constant. That means that the separation between two spin. J is the exchange term. Exchange energy actually. So what it defines, that how strongly they are, coupled with each other. And then V prime is that number of spin per unit volume. Into. Okay, so this is A. Fine. Which we is something very fundamentally related with the. Then I will introduce another term. So if we keep on what do you say, keep on creating a lot of domain wall, then what we need to have some sort of a energy addition. So that energy addition is known as sigma dw. This is domain wall energy density, and then pi r square. I mean, let's say consider it, it's like a sphere. Okay, so sphere has been split into two parts, and if this is having any radius r, so the circle which it will form is having an area pi r square. And then in order to create it, okay, the domain wall, some sort of the reduction is also going on there. So that is 4 pi r square, which is the surface of everything. This is demagnetizing field, A k to the power half, where k is known as anisotropy constant. What is anisotropy constant? I will just explain it to you. Give me a minute. So when people studied, okay, so when people studied that, they found that it's easy to magnetize iron in a particular direction with respect to another direction. Okay, so it gets magnetized in 100, and then in case of 111 direction, it's very difficult to magnetize. 100 and 111 are the crystallographic directions. Okay, so that means that there is an if we go from one direction to another direction, if I try to move my spins of all the alignment in the material from one direction to another, it will cost me some energy. Okay, so when this energy is equivalent to domain wall creation energy, because everybody was happy in this direction, but now we are orienting it from one direction to another direction in order to create the domain wall. So it will be costing some energy as well. So when this become equal, and then if I keep on reducing r at one point of time, the creation of the domain wall is not favorable anymore. Okay, so when it's not favorable anymore, the system say that I will not create a domain wall. That means that, remember that my original requirement is that we have to keep on reducing the size in order to pack more and more. Okay, so if I keep on reducing the grain size, okay, at one point of time the system says that, well, I will not create any more domain. I will stay in a single domain state. Okay, you can note it down the keyword, and then later you can read about it. So with reduction of size, Why we need to reduce the size? Because I have to pack more and more data. Okay, so with the reduction of size, the particle becomes single domain. Okay, when it becomes single domain, that means that every spin is in a particular direction of, let's say this is my particle, there is no domain creation, everything is in a particular direction. Is that okay up to this point, that there will be no domain, everything is in a particular direction? Fine. Class, this concept is little tricky. So there is no domain. That means that if I pick up a grain on which I have regarded my bit, so every spin is in a particular direction. Is that clear? Okay.
Yes, sir.
Okay. So I mean, if I keep on reducing the size, I mean, I have to remember that the driving force is that I have to pack more. So at one point of time, so in order to go from this size to this side, we just create a barrier. So let me write it down for you. And then why it was not possible to pack more and more, that we will try to understand. So everything is in this direction, and then I can write it down, some energy equations. I will not write it right now, but then I can apply something, some force, some field, that I can switch it in the another direction. Okay, so from here to here, so if I'm going it, so it will not suddenly go from here to here. Okay, so this is going as changing the sign. This is, if this is theta equal to 0, this is theta equal to pi. Okay, and in order to go from one direction to another direction, it has to pass through a barrier. Okay, so this will be like this, and this function is something called Ku cos square theta. Okay, cos 0 is 1 and cos pi is, so this is square, so this is also 1. Okay, and this is the negative direction somewhere around. Okay, so that's what happened, and then this is something called a barrier height, which is equivalent to Ku times V. Okay, so Ku is known as anisotropic constant. These are the expressions, but in order to make your life simple, let me explain it to you again. So what we were having everything in a particular direction. So this was the direction, and then in order to go from this direction to this direction, it has to cross this barrier. Okay, so if we are by some means doing it, so some energy get consumed. Let's say that I mean all the application is at room temperature. Fine. So let's say that this barrier height is so small that the room temperature energy is sufficient enough to flip it from one direction to another direction. Okay, so that's very much possible, that the thermal energy is sufficient enough to bring all these guys from this direction to this direction, and this height is less than the thermal energy. Okay, so if the thermal energy is bigger, so automatically it will be flipping from one direction to another direction. Remember that this was my green. If this was the direction, thermal energy is sufficient enough to flip it into the other direction. Okay, so my 1 become 0. Is the problem clear to you, that what is happening down there with the reduction of the size?
Yes, sir.
Okay, so now my data is not anymore safe. Fine. So what we have to do, I have to pack more and more. So I have no room to play with the volume. Okay, so, and thermal energy is going to be fixed because I have to operate at T equal to 300 Kelvin. So the only room which is left here is that we play with the anisotropy constant. That means that if I somehow, tailor a material which is having a high anisotropy constant, then I can pack more data. Is that clear? Because I have to have a very small volume. Okay, volume I have to go down. So the only way to compensate it that I have to increase the KU. Is that clear? In order to increase this barrier height, I have only possibility to increase this anisotropy energy. All right.
Yes, sir.
Okay. So I had 5 requirements for the material to be deployed as a magnetic retarding material. Okay. Now there is another parameter added to that. If you have noted it down somewhere, you note down the 6th parameter as high anisotropy constant. So we added another parameter for the high density retarding. Okay. Clear? So now there are 6 filters, and there are only few material which qualified in the all categories. Okay. So if you can work in this direction, and if you can find it out another candidate, you will be a billionaire very next day. Okay, and don't forget to tell this to the student. Okay, of course there are many more complex physical phenomena involved deeper, but these are the 6 key criteria which is being used as for the selection of the material to be deployed as the what do you say, as the magnetic retarding material. Fine. So I will suggest you to note it down few keywords. One is called superparamagnetic limit. Okay, try to read it. There is a lot of material available. Okay, you will learn few new keywords. So that's the one part of the lecture. Okay, that we know that these are the 6 things which is needed. Now there is another part which enables us to read it. Okay, so what is now here that we have coming back to my original recording, this is the small strip on which we have recorded it. Okay, so 1 0 1 0, so 1 0 1 0 is down here. So how it will be, or let's say in case of, it's easy to understand in case of a longitudinal one. So this is like this is like this. Magnetic field line will be in this direction. In case of magnetic field line will be in this direction. Okay. So we pause it for a moment here. Okay. Note it down somewhere. We come back to this. Let's try to see a scene. So you might have experienced that the resistance is because of, why the resistance is there in any material? Can anyone answer this question? What is the origin of resistance?
So collisions.
Collisions of what?
So the charge carriers face collisions in the material.
Atoms and molecules, sir.
Atoms and molecules and defects and everything else. Okay. So don't call it collision, we call it scattering. Okay, that is a better word. Fine. So there is a scattering of charge carriers. Okay, with the another charge carrier with surface, with many more things. But what we forget in case of the electrons, that they have the spin also. Okay. So let's say that I have a magnetized material having direction magnetized in this direction. And then there is another layer which is having magnetization in another direction. We have both spin up and spin down electrons. Okay, so when spin up electron is entering here, it is seeing a similar kind of an environment. It doesn't need to flip its direction. So there is something called R up. But when it goes here, it has to flip its direction. That means that another scattering or another phenomena is added, so that there will be another different resistance because of the magnetization direction orientation is different. This is called R anti-parallel. This is called R parallel. Okay. So similarly for the another guy. So if this spin down is going down, then we have R spin down and spin up, and then we have R spin down, spin down. So let's try to see that what these different resistances do. Okay. So let's say that R parallel, which one will be larger, R parallel or anti-parallel? Class, which resistance will be larger? If they both have, I mean, this spin is coming here and then see the similar kind of environment, will there be an additional scattering, or there will be additional scattering when spin down is there? Okay, I tell you that spin parallel is less, spin anti-parallel is, okay, so this is also parallel, spin anti-parallel is bigger. So if such a scenario is there, okay, I will create two scenario. Okay, so this is scene one, right? So let's write it for spin up, spin up.
Yes, sir.
Yeah.
So resistance will be more in anti-parallel.
Yeah, resistance will be more in anti-parallel. Good. So I'm going to write it for spin. This is for spin up. So this is smaller. This is bigger. Okay. And then for spin down one, this is the bigger resistance and this is the smaller resistance. So let's say that this is 10, this is 100 ohm, this is 100 ohm, this is 10 ohm. Can you quickly give me that what will be the effective resistance of this whole assembly? 55 ohm, good. Okay. Let's say by some means I have flipped this in this direction. Okay. So my circuit changes. So now these both are small. For spin up, this is 10, this is 10, this is 100, this is 100. Okay. Can you tell me the resistance of whole assembly now? So this is 20, this is 200. Someone please calculate it quickly for me.
$18.18.
18.18. So remember this. Okay. Now I'm going to move this whole assembly over a already recorded material. Okay. So here we are, substrate. One guy is in this direction, so that means that the field line is here. Half of this guy. Okay. And now it will be, the spin is in the, sorry, the magnetization of this layer will be, so this is already there. Okay. And the field lines are here. Okay. So now this is one scenario when there is one. Okay. I move everything over here. Now the field direction in this direction, and the whole assembly is like this, because this is a pinned layer or far away layer. It will be less affected, and then the lower layer get oriented in another direction. Is the both scene clear to you, how they are different? Class?
Yes, sir.
Okay, so this was how much? 55 ohm and this was 18.1 ohm. Okay, so with this difference and with a lot of electronics, one can distinguish between 1 and 0. Okay, bigger this difference is, bigger my reading capabilities are. Okay, so now I need not to go back to my solenoid thing. Okay, I can deal with, with this kind of a system. So this whole thing is known as giant magneto resistance based reading head. Okay, so the principle is there. Okay, you note it down the keyword and read a bit deeper. So now I'm here to take, okay, so now coming back to, why this high saturation magnetization is important. Bigger this, the magnetization of this material is strong, it's easier for it to, read or get, orient that layer magnetization. So let me show you some more slides and then we will take up the question. So here we are. As we are increasing the size packing, okay. So for 6 gigabit per inch square, the size needed is 15 nanometer mean size. But as we are going down here, then we have to, deal with a 100 nanometer mean size. And it's possible to, synthesize such particles and pack down there. So here you may see it, they are going along some line. Okay, so a track is being formed and one can record more and more. Okay, so in order to record it, such a kind of an assembly small electromagnet is needed. Okay, so you apply an current direction, the magnetic direction changes and you orient it in a particular direction. Okay, so depending on the current direction of the, what you call solenoid, or this language, the binding. Okay, one can change the magnetic direction and then one can record these guys in a particular fashion. And in order to re-record it, okay, one need to erase it first, so it randomized, then you kind of recording. So it's moving like this. First the erase head, move it, make it total kind of no magnetization, then it's easy for it to record it. All right, so that happens. This we have already discussed it out. This we have also discussed this out. So these are the domain wall configuration which we talked about. Okay, so from one direction to another direction there is a whole chunk down here. So these are the domain wall zones, okay, which one has to consider while designing all these things. So this is the spin down, this is the spin up zone. So 1 0 1 kind of a scenario get created over here. Multi-domain is with reducing the size, we still ferromagnetic here, but at one point of time there is no fixed direction, so it behaves like a paramagnetic, but magnetic ordering is there. This is super paramagnetic. EG direction we have already talked about. This is not for the iron but for the nickel. This is also we talked about from one state to another state. If we apply a magnetic field, this jumping probability is is different. And then this is the reading part. Okay, so one is pinned, then there is a conductor help in coupling. This is the free end, and one find a difference between two states which we talked about, and then sometimes these differences are quite high, up to 80%, so it's easy to discuss it out. This you have already seen. A ferromagnetic layer is separated by the non-ferromagnetic layer, so the different assemblies are down here. And that's it. I'm now open to have the questions. Rajan?
Yeah. Questions, fellows?
Yes, sir. Sir, how is this protected from stray magnetic fields? I mean, suppose when we are using it somewhere and some magnet comes nearby, then
Yeah.
that orientation will get disoriented and data will be lost. So
Yes.
how it is protected from?
Okay, so generally the data is protected by a magnetic shield. Okay. So magnetic
Okay.
shield is another kind of easily magnetizable material, okay, which can be easily demagnetized also. So the field line get, you know, kind of blocked by these easily magnetizable materials. So there's something called magnetic shield, and they are
Okay,
soft
okay.
magnetic material. You make the layers of magnetic shield, and then it's slightly away from the data. So it's a magnetic field. I mean, one layer of protection is this, but if it's really strong, okay, it will penetrate the magnetic field as well and then go and destroy your data.
Okay, okay.
You might have seen
Sir,
yeah.
Yes, sir.
You might have seen in the movies, na, they are generating an EMP pulse and destroying the electronics and all, right? It's the
Right.
same thing happened there also. Yeah.
Okay.
Next question.
Okay. Sir, and on this surface, is there any static electricity effect? Like, suppose some static comes up, so will it disorient or this is immune to static?
No, for the static charge building up, which surface? The recording surface or the reading
Yes.
one?
No, sir, recording surface.
They are immune to kind of. They are highly insulating materials actually. The kind of material which is being used, they are very insulating in nature.
Okay,
So,
okay.
so it's very difficult to build up the charges. If the charges do get built up by some means, then it's very difficult to get rid of also. But
Okay.
as far the
Okay.
magnetization is concerned, there will be slight change, very small influence, but it is not going to affect the capabilities.
Okay, got it. Thank you, sir.
Anyone else?